All right, so let's classify some patterns. All right, so what I'm going to try to do here is, in the name of talking about images later, we are going to do an example where we learn a classification task over a slightly, good Lord Almighty, I can't write. All right, over a let's say non-trivial data structure. Okay, so I'm going to learn to classify an interesting sort of non-trivially structured input. All right, and by non-trivially structured, I just mean not 1D, right? Multidimensional like an image. Okay, so here's my input. And we can see, so I am using Keras, so this is intended to be the input for a Keras network. I have an outermost, right, I'm packing this into a NumPy array, and I have an outermost index, right, where every place on the outermost index corresponds to an input. So what I mean by that is inputs 1 is still going to be a training sample, and inputs 2 is going to be a training sample. That training sample is just going to be a 2D array instead of a row, right? That means that inputs has 3 indexes total. It is a 3D array, right? Where index 1 is the sample, index 2 is the width, is the height, and index 3 is the width. Okay? Now, notice what these are. These are little, tiny, 2-dimensional arrays of floating point values between 0 and 1. We can kind of think of these as little bitty, tiny, 5 by 5 grayscale images. Sorta, kinda. Right? Why grayscale? Because there's one channel, right? If we wanted it to be color, we would need to have 0, 1, 0 right here. Something like this, right? For red, green, blue. But that's a little bit more non-trivial than we want to deal with right now. So right now, we're going to deal with these little bitty, if you will, grayscale images, right? We can kind of think of the value 1 as being fully on, and then 0 as being fully off, right? Brightest intensity, lowest intensity. And the first one, if we were to plot it, see that I've put the 1s on a diagonal, so we get an image like an X. The second one, if we were to plot it, would be an image like a diamond. See? And then the third one, again, if we were to plot it, would be an image of a plus. A little bitty, tiny, 5 by 5 pixel black and white image of an X, a diamond, and a plus. Okay? So that is the input that we are about to learn to classify. All right? And I just realized that I keep leaning backward and forward, and I hope the volume of my voice is not changing levels dramatically as I do that. Yep. So food for thought, these images are really teeny tiny, okay? How many inputs would be involved if I had a larger color image? So large here really deserves its own quotes, right? Because by modern standards, is a 64 by 64 pixel image large? I wouldn't say so, right? But how many inputs would be involved there? Well, 64 times 64 times 3. That's a lot of inputs, right? So for some of the simple problems, we were able to think about our input as a 2D space because we had 2 inputs, right? For these larger image problems, we can't really visualize them that way because they are a 3 times 64 times 64 input problem. And it's going to bug me. So let me find out how many that actually is. GNOME terminal, oops, BC, the binary calculator. Why did my system hang? 64 times 64 times 3. All right, so 64 times 64 times 3, that is 12,288, right? So our intuition of a 2D space breaks down a little bit when we jump to a 12,288 dimensional input, right? Or does it? Because it's actually going to turn out that some of our intuition about how things work and don't work and why can actually survive fairly well from being mapped from a 2D or 3D space to a 12,000 dimensional space, right? The sort of intuition we built up about sort of producing an output surface still can kind of work in some ways. But we have our 64 by 64 by 3 images. I'm sorry, we have our 5 by 5 by 1 images. And here are our 3 labels. And we see that once again, I have assigned, they're 1-hots, right? And I have assigned 1 to the X case. And sorry, 1 in the second one to the diamond case. And then 1 in the third place to the plus case, right? So this one is getting 0, 0, 1. This one is getting 0, 1, 0. And then this one is getting 1, 0, 0. And remember, Keras likes its inputs and its labels in potentially 2 different NumPy arrays, and we associate one sort of row, right, where all of this is sort of one index to one row in here. See that? All right, let me redraw that so it's a little easier to see, all right? Where every outermost row in this array goes to a row of this one. Yes? And so, okay. Now is an acceptable time to pause the video if you're feeling a little bit lost and really kind of meditate on this, right? Yep, we already talked about that. Good. Yep. So here is the Keras network we might use. So a couple of things to note. Notice that I have given my input 2 indices, right? In the code that you have now, you have something like this, where the input is size 3. Here, I've given it 2 indexes, right? Because our inputs are those square 2D arrays. But the first thing I do, come on now, there we go, is flatten it. What does that do? It takes all of our indices and flattens it to 1. In this case, 1 25 length input. Then, with my 25 size input, excuse me, and notice I didn't need to tell it what that number was, it figured that out. With my 25 size input, I can build a normal feed-forward network. So, very, very loosely, you might wonder how I picked size 20. Essentially, what I'm doing is trying to narrow my network a little bit at every step, okay? The very loose intuition I'm using here is that we want to narrow a little bit to make our network learn abstractions, okay? So the neural networks, I guess, they're only really doing something interesting when they are learning to build with abstractions. And forcing them to deal with decreasing amounts of information forces them to build powerful abstractions. That's basically the idea, right? So we're narrowing a little bit as we go. We don't want to narrow too much, because then we might throw away too much information. We don't want to expand, though, or we don't want to not narrow enough. We certainly don't want to expand, because then we might have that capacity problem, right? We don't want to use way more capacity than we need. These decisions are, so that my decision to go 2023 is not really based on any deeper reasoning than that, right? It's just want to narrow a little bit, don't want to narrow too much. Figure we'll probably need maybe we might need a bendy layer, or a fairly bendy rule here, so we probably should have at least 2 hidden layers. That's basically it. And in practice, in the real world, you just kind of get to experiment with these things and build up that kind of intuition, and then try different sizes of network to see what is going to fit. And we'll revisit this when we talk about hyperparameters, right? Maybe I can't spell parameter, I don't know. And they also have just given you a cliff notes of that discussion. We'll see. All right. So notice for the time being that I am using the hyperbolic tangent as my activation at every layer. And notice that my last layer has size 3, right? Inputs had size 5, because that's the shape my inputs were. My last layer is size 3 because that's the shape my outputs were, where every column there is going to correspond to a label. Yep. And then here I just use, right, we've seen this code before, right? This is pretty much unchanged from the example you have, where I'm going to use stochastic gradient descent, mean squared error loss, and then fit for a bunch of epochs. And maybe we should look at that code in action, shouldn't we?